Uh, my name is Lily, and I'm a master's student at the Harvard Extension School and a student intern with the Massachusetts Open Cloud and Red Hat.
I'm Emre Ates. I'm a PhD student at Boston University.
And today we'll be telling you a little bit about the Pythia just-in-time instrumentation framework that we are building. This is an ongoing research project between the MOC BU and Red Hat. And it's a very high-level introductory overview, so if you are curious to learn more at the end of our presentation, please do come see us at our poster. So that is our topic, but what we'll really be talking about today is your future self interacting with a distributed system in which you're grappling with a mysterious problem. So stay alert and use your imagination. In the near future, it is a dark and stormy night. You've stayed late to finish a very important project on a distributed system that you're familiar with, perhaps OpenStack. And everything is going well until you see that the same requests that you've been issuing to this system that normally take less than a second to complete are taking longer and longer, 5, 10, 15 seconds. This is really disrupting your work, and you need to fix it as quickly as possible. But what can you do? Unfortunately, it may be difficult for you to debug this problem in your distributed system. And this is because in a distributed system, there's such a vast number of components, any one of which could hold the root cause of your problem. Although you only see 3 components here on the screen, you know that in a real system, each of these components could stand for dozens or more. Additionally, on all of these components, you have to contend with multiple stack levels. So, for example, while you may be experiencing the problem in the VM where you're working, the root cause may actually lie in the hypervisor. Who knows? And just to make things even more complicated, it could also be the case that no one component or stack level holds the cause of your problem, but instead the problem only arises in the interactions between specific components, represented here by these crazy arrows. So you've got a big problem on your hands. Now, at this point, you get to choose your own debugging adventure, in a sense. So on the one hand, you could use traditional debugging methods to get to the bottom of this, and on the other hand, you could use the Pythia just-in-time instrumentation framework. So first, we're going to explore traditional methods and see how that goes. So in the traditional debugging cycle, you have some instrumentation in your system that gives you data about the system's state. And you hope that this tells you something about your problem. But you don't have instrumentation everywhere in your system. This would produce far too much overhead and give you an overwhelming amount of data to sift through. So what you have instead is some number of components instrumented that someone thought would be generally useful at some point in the past. Unfortunately, in this case, as is often the case, this current instrumentation doesn't give you enough data to identify the root cause of your problem. So what do you do? Well, what this typically looks like is that you use the data you have to make a guess about where to add more or different instrumentation in your system. And you might have to do this an arbitrary number of times, over and over again, trying to narrow down the scope of where your problem might be. And as you're doing this manually, you have to not only determine where to add instrumentation, what data should be gathered, you have to go in, manually add this instrumentation point, perhaps having to recompile and reintegrate that component into your system. So as you can see, this is a huge time sink. And on this dark and stormy night, trying to investigate your mysterious problem, you have a huge headache. If only, you think, as you look out the window into the storm, if only the system had a way to automatically determine where instrumentation points could be useful for this current problem. And if only the system could automatically enable these trace points, or these instrumentation points, without someone manually having to go in and write brand new ones. Let's stay with this train of thought as we explore the other potential branch of our adventure, the Pythia just-in-time instrumentation framework.
Yeah. So in the next part of the next fork of the adventure, we are using Pythia to automate the debugging cycle. So in our proposed framework, before the engineer, Pythia actually investigates the traces and locates problematic areas. And in these problematic areas, Pythia enables trace instrumentation that would help locate the problems. And it also disables the boring instrumentation, which doesn't give us any new information or that would cause extra overhead and extra things for the engineer to look at. So here's, for example, how one cycle would look like. And then Pythia repeats the cycle to enable more and more granular instrumentation while disabling unnecessary instrumentation. And the engineer only inspects these lean traces that we get at the end that include information about the potential problem, and then they only need to fix the problem. So the part that is painful to recompile the whole system, include more trace points, and then get more data is skipped. So we have a couple of key insights and enabling technologies that help us realize Pythia for the distributed systems of today. The first one is the insight that high performance variation among requests or commands that are issued to the system are expected to perform similarly. So these high performance variation in similar requests would be an indicative of problems. So Pythia can localize the performance variation to identify where additional instrumentation is needed, and then it can enable necessary instrumentation points with this insight that high performance variations are usually indicative of problems. So for example, if we issue a bunch of requests to this distributed system, which has 3 components, it's OpenStack, and then we get this performance distribution out of our request group. And if there's a problem in one of the one of the components, then we would get a bimodal distribution where some traces experience the problem and the other requests don't experience the problem. And by looking at this, we can actually find out where we need additional instrumentation. Another key enabling technology for us is end-to-end tracing. So end-to-end tracing is currently being used in most distributed systems, and it can be added to the ones that don't use it. So how end-to-end tracing works is for each request to a system, we generate a unique request ID, and then we propagate this request ID alongside each of the commands that are sent to the different components. And then each of these components actually log necessary information into a common trace database with the request ID attached to it. And then we can collect these traces with the common request ID and then reconstruct a workflow of an individual request that looks like that directed acyclic graph on the right-hand side. So let me go into more detail about the workflow of Pythia. First, we gather the current request skeletons that using end-to-end tracing that I just described. And then we extract the critical path from these skeletons because components that are not in the critical path are not causing a performance problem for us. Then we group these skeletons based on the similarity and based on whether their structure is identical or not. Then we can group these, then we can calculate the performance variation within these groups, and then we can localize the performance variation to specific points in the graph or edges. After which we can determine what instrumentation to enable by looking at what is the extra instrumentation that we can enable that's on that edge. So I talked about performance variation now, but another thing, way to localize where to add traces could be consistently slow groups. So we may just want to find out where our time is being spent for each request. So currently we are exploring the applicability to OpenStack, and we are eventually going to explore Ceph and maybe other distributed systems. And we are augmenting OpenStack's tracing system to support Pythia. And our prototype code base can actually identify and localize high performance variation, and we are testing on simple OpenStack problems. We plan to deploy this on MOC and then see how in a production system the traces look like under real problems. Some research questions that we have that we are going to look at next is whether there are other metrics that can predict where instrumentation may be needed besides variance and latency. And another interesting question is, what is the minimum level of instrumentation for Pythia to begin its analysis? And what is the stopping condition for this analysis cycle where we enable more and more granular instrumentation? A more high-level question is, what is the relationship between the strategies that we use to enable these traces and Pythia's output? And what kind of output is more useful for engineers, and what kind of algorithms result in the output that we want? So thank you for listening. And we have a poster outside if you have any more questions.